On January 13th, 2025, a team of college students in the aeronautics engineering program awaited their semester project assignment for senior design. Years of learning had built up to this point over various different aircraft disciplines. What could this reverse engineering project be? A fighter aircraft? A helicopter? A glider, perhaps? Perhaps not. The professor walks in on the first day, enthusiastically informing us that the future is in the stars. Not long after, the project was assigned to reverse engineer the current version of SpaceX's Starship and prove the feasibility to make the journey to Mars and back while being fully capable of transporting human life. With only a single semester of astronautics under our belts, the only thing I can think was perfect. However, the time of fear did not last long, as the work process, and more so the learning process, was now afoot in order to be able to successfully complete the project and pass the class. Our team of students began working from there, and we spent our days and nights, our long nights, working together to be able to pull this off, and on April 27th of 2025, the project was finally due. To all our surprise, we did manage to complete the project in the nick of time, marking the end to our semester and finally being able to get more than 4 hours of sleep. As you can see on your screen, this is the team's finalized results to the conceptual design of the reverse engineered version of current Starship. The results themselves are not that intriguing, as they are very similar to current Starship design for obvious reasons, since this vehicle is already being designed for the purposes outlined for this project. In this video, I will be describing loosely the process that the team has undertaken to complete this project, as well as summarizing some of the work that I personally have done. This video is mostly because for the past 3 months I've locked myself behind a door doing only this, and it's all I have to offer. So please show some support, and I apologize in advance if you catch me having another hiatus for various other projects in the future. One last thing, before we begin, this video will be made as simple as possible. So for those of you chillin', it's perfect for you, but those of you students looking to grab some information on something, this video won't be very helpful. With all that done, let us begin. Earlier, you may have caught me using the word conceptual design, and that is exactly what this project is. It was a conceptual design project. Conceptual design is the early stages for inventing or creating something, whether it be reverse engineered or brand new, and it can be seen as the stage in which you prove or disprove the feasibility of something based on the required design parameters or just logic. If a customer was to ask you to build an aircraft that can produce aerodynamic lift without any aerodynamic surfaces, whether it be wings or just the body itself, then logically you can look at the customer and say, hey, that's not possible because aerodynamic forces are produced via aerodynamic surfaces. And boom, that is the completion of conceptual design. Now, the customer can either leave or can make adjustments to their request to actually make it feasible, in which you start from square one and begin actually designing the thing to create the internal and external layouts such that their requests are met in the most monetary efficient way possible. Hopefully. Now, you may be wondering why it's called conceptual design and not just design, and that is because conceptual design is a small component of the entirety of design. Design generally has 3 different phases, being conceptual design, preliminary design, and detailed design, and they are completed in that order. Preliminary and detailed design are more focused and specific in what they have to offer, and as such, their results are more accurate than the conceptual design phase, especially since they use higher order equations in software such as the Navier-Stokes equations and ANSYS and whatnot. They need this because they analyze very specific components and ensure that every screw, nut, and bolt will be acting as expected and will not cause any issues to the system. Which means that in terms of the finalized blueprint for actually building the product, they will be making that because they will have the most detailed information to do it accurately and safely. However, they cannot do their jobs without the aid of conceptual design. This is because those higher order equations and software need to have countless inputs in order to run, such as geometry, the flight conditions, the weight, and so on. Well, how do we get those inputs if the vehicle isn't designed? Well, that is the job of the conceptual design team. The conceptual design team uses lower order equations and sacrifices accuracy for speed because while ANSYS may provide results of 99.99% accuracy, it takes 12 to 24 hours to run a single aerodynamic simulation. A lower resolution method like Vortex Lattice method can also be used for 85 to 95% accuracy, but can run hundreds of simulations within seconds. Instead of analyzing every nut and bolt, the conceptual design team ignores those finer details and creates and analyzes the simplest version of the model, and will run through hundreds, thousands, or even tens of thousands of different possible models and then choose the result which they deem to maintain the most amount of pros while minimizing the amount of cons. The results that the conceptual design team produces for the geometry and trajectory of the vehicle is then given as inputs to the preliminary design team to run their more accurate softwares and analyze those required finer details, and then those results are provided to the detailed design team, and you get the gist. Once all that is completed, a prototype is built, tested, any last second changes are made, and then the final product is completed, which will either thrive or fail, depending on how much better or worse your competitors' designs are, and thus is the world of engineering. Or at least that's what I'm told. Since we are doing conceptual design for this project, you can imagine the level of detail produced within our submitted project. We know the overall dimensions of the vehicle, both internal and external, and we even somewhat accurately know the trajectory, aerodynamics, controllability, and even cost of the vehicle. However, we do not know the effects of more finer details and are incapable of producing a blueprint which can be provided to manufacturers to actually build the thing. But now let's get into how we actually reverse engineered this beast. One thing that every member of the group had to do, regardless of the disciplines they corroborated on, was something that was referred to as literature review. Literature review is a fancy way of saying research. Since no one on the team had any experience in launch vehicles and spacecraft, we were all very accustomed to it because we all had to learn everything we could about these types of vehicles, how they related to our disciplines, how to actually derive what we needed, and so on. The types of research I conducted and where I got most of my information first and foremost was textbooks in both graduate and undergraduate courses, followed by NASA documentation, and surprisingly, a lot of .mil websites for rockets. .mil is just the US military domain, and I was bewildered. You'd be surprised how much good stuff I was able to read and use for my project. I would have sworn some of that stuff would be classified, but nope, it was just in the public domain. But honestly, it just made my life easier, so I'm not complaining. Now comes the actual analysis for the reverse engineering process, and the first step is to define what the goals of the vehicle are. In our case, it was where we wanted to go, how long we wanted the journey to take, how many people it would be capable of bringing, and so on. With that information, we can perform something referred to as convergence, which is nothing more than a very sophisticated iterative process. Essentially, all the requirements that we listed earlier for what we wanted the vehicle to be capable of doing are made into variables. For example, if you wanted to make a crewed mission, you would need systems on board for them to live, such as air, food, water, etc., and these weights are defined in units of mass per crew member. This is also done with the weight of the electrical or telemetry systems on board, the expected structural index values, and so on. These variables are acquired through literature review, either through methods of calculation or through historical models of what previous missions have provided in the past. Unfortunately for us, most companies, including SpaceX and Blue Origins, are very tight-lipped about their data, which forced us to use older accessible data, mainly the Apollo missions and Space Shuttle. But when we have all those values defined, we could perform the convergence method. The convergence method we utilize focuses primarily on hypersonic vehicles, as that is what our vehicle performs at, and these mathematical models allow us to create a solution-based prediction of what values our finalized vehicle may be allowed to fall within, assuming that the numerical values you acquired previously are accurate. Creating a program that inputs your found values and some iteration parameters allows you to solve those equations and produce a solution space for what takeoff gross weights, planform areas, thrust to weights, and other values like allowable payload, dry weight, and so on are feasible. Anything that is not within the solution space is not capable of completing the mission. That doesn't mean you can't build it, but you're just wasting your time. Good news for us, because a sanity check of if we were on the right track was to determine whether current Starship falls within these results, and as you can see, it does, meaning we are currently doing fine. Now, this stage doesn't design the vehicle at all. Matter of fact, we haven't designed anything up until this point, as there is no vehicle. All we know is the limits of how heavy, how much area, how much thrust, and other factors we are allowed to make before we know the vehicle isn't capable of completing the mission. This is important because we need to know the budgets of what we are allowed to do when we start designing. For example, there's a clear weight budget that the vehicle has, which we can't exceed. Now, that seems intuitive since lighter also means cheaper, but there are other factors with upper and lower bound limits, such as the volume budget, which doesn't necessarily have a direct link to cost, but are vital for the vehicle to be feasible based on our solution space. Now we are finally ready to begin designing the vehicle, right? Well, almost. See, we can't design a vehicle if we don't even have an idea of what it might look like. In our case, we are reverse engineering an already existing product, so we have some idea. However, if you were creating something brand new, then there is no approximate image for your brain to latch onto. Therefore, we need to create that image, and the only way to do that is with more research. Even when you're creating a new product, it's not as if you're creating something that no one has ever seen before. That's just not how humanity progresses. It's likely that there are other products or vehicles that, although not capable of doing exactly what you're designing it to do, may have a lot of overlap, which you can use for reference. For example, if you want to build a brand new stealth aircraft, you would examine other existing stealth aircraft, both past and current. These vehicles will have airfoil shapes, chines, geometry, and other features that are commonly shared, and it's for good reason. For example, stealth planes have sleeker bodies with chines and S-shaped inlets that aid in minimizing the RCS, which improves stealth. These features may not be seen in something like fighter aircraft because they are more so designed for pulling more Gs, being more maneuverable, and so on. Therefore, the idea is to look at different vehicles, understand what components, geometries, and technologies they had on their vehicles, and why/how that aided in their performance, which is similar to what you are designing your aircraft for. Then you can combine all these ideas to get a general idea of what your vehicle will look like in an OML sketch. Now, these aren't concrete. It may be that when you are performing your analysis that you find something else fits better, and you will change your OML sketch accordingly, but starting with a rough draft and refining it further is to be expected. Fortunately for us, when you're reverse engineering something, you already have that vehicle which you want to compare it to, so all we did was analyze the necessary components to its performance for Starship, gave the reasons of why we continue to stick with this design over other designs, and then created our OML sketch of what our vehicle will more or less look like when our conceptual design has been completed. Finally comes the actual analysis, where we actually create the vehicle. Now, it seems like it took a lot to finally get to this point, and it did, but it was all necessary in finding out what we can and can't do when designing the vehicle. My disciplines for this project were stability and control, as well as structure and material. For structures and materials, it was my job to make sure that the vehicle can survive the loads in which it experiences throughout the journey, and while I must ensure that the vehicle can survive it, I must also not make it so bulky that it doesn't fit the previously listed dry weight budget. Furthermore, to do a structural analysis, I need to have a geometry for the vehicle which can be analyzed, and thanks to the OML sketches from the previous phase, I have just that. So, everything that we have conducted previously is of utmost importance. Now, since I was only in the two previously mentioned disciplines, I will discuss the analysis within only those two, since I had no hand in developing the other discipline strategies. Even more than that, within these two disciplines, I only had specific tasks. For example, in stability and control, I only analyzed the stability within space, as well as the controllability of the vehicle throughout all phases, while my discipline teammate derived the stability of the vehicle in atmospheric conditions. For structures and weights, I located the center of gravity of vehicle throughout the entirety of the mission and discussed the survivability of the structure based on applied forces, while my disciplined teammate analyzed the survivability of the structure based on the experienced temperatures. Starting with stability and control, I first analyzed the stability of the vehicle within space, and it turns out spacecraft stay stabilized by spinning and by using gas thrusters. The reason they stay stable while spinning is due to the gyroscopic effects as well as the conservation of angular momentum. After a bit of derivation, I found that the vehicle can only be stable if it's spinning on its major or minor axis, which, for reference, the minor axis for a missile-shaped object is the long axis, and the major axis is about its size. While this may sound perfect because it suggests our vehicle can spin about the long axis, which is ideal, there is a caveat. This is only true for purely rigid bodies. If the vehicle has any flexible or non rigid components in its system, this is not true. We can confirm this with a bit more derivation, which suggests that for vehicles that contain non rigid components, the only axis in which it can naturally spin stably is about its major axis, which is not ideal for our design. This was actually confirmed in 1958 when Explorer 1 was launched, and it was shaped similarly to our design and it spun about its long axis. However, because it had non rigid tethers on its sides, it eventually began spinning about its major axis and began tumbling out of control. This is what is now referred to as the major axis rule. Since our vehicle will contain propellant and oxidizer fluid within it during its space travel, which is non rigid, that means our vehicle cannot be naturally stabilized via its geometry alone. Fun fact, this is actually why many satellites are made pancake shaped. Because in that flat disk shape, the major axis is about the short center axis, meaning they are naturally stable by design. Our vehicle is not pancake shaped, and therefore it needs to either forcefully be made to be stable via devices called control moment gyroscopes, which artificially creates the major axis about any direction using the conservation of linear momentum. However, these are very heavy and require many of them in order to be viable. Therefore, we utilize the other method where the orientation is manually controlled, and this is utilized on many spacecraft that are similarly shaped to ours. In space, there is no atmosphere, and there are not many forces that will naturally disturb the orientation of the vehicle, and those that do will do so over the course of a large period of time until that momentum builds up. Therefore, when a spacecraft has its orientation disturbed enough, it will excrete some gas in the opposite direction it wishes to face, and based on Newton's second law, it will produce a counter torque to undo any buildup. Furthermore, two excretions can happen on opposite ends in opposite directions to spin any direction it desires. These gases can either be from the Boyle law from the tanks of the vehicle, or in many cases, the spacecraft will have gases in its system just for this purpose. The Starship uses the second method, and the gas thrusters are in the shape of the cowbells on its side. These are positioned and angled accordingly so that the vehicle can rotate and spin about any axis with the minimum amount of thrusters possible. As the saying goes, if it ain't broke, don't fix it. So, our analysis concluded that our finalized product will utilize these same control systems for space travel, as it is more than adequate for our purposes. Now, finding the controllability of the vehicle in the atmosphere was a much more daunting task, as in the atmosphere, the aerodynamic torques applied are significant, and the vehicle must be capable of maintaining attitude control throughout all 3 degrees of freedom at all the required altitudes and velocities. Because there are a lot of phases in the mission that encounter the atmosphere, I will not walk through each one individually, nor will I walk through pitch, roll, and yaw individually, so I will describe it in a general enough sense that it encompasses them all, since I use the same method for each axis of each phase. In order to analyze this, we need the aerodynamic coefficients and the aerodynamic centers provided by the aerodynamics team, as well as the center of gravity locations provided by me. With these inputs, we could technically code up an ODE simulation of every phase with a PID controller and run it and see if it passes or fails, but that just sucks and it takes a lot of time. I actually did that for our vehicle entering the Earth's atmosphere, and it took about a week to code, and it took 15 to 20 minutes to run a single simulation, so that idea was too high order, and it was just a sucky process in general. But there is a better way to check for controllability, and that is utilizing the control ratio. The control ratio is very simple. It's just the torque which the vehicle can produce for control divided by the torque which the vehicle produces naturally. If the control torque is greater than the natural torque, then the vehicle is controllable. Simple as that. Of course, I can't just make sure that the control torque is only slightly higher than the natural torque, so I set up conditions that are generally used even for launch vehicles. The conditions I checked was that for every phase, for every axis, that even at its worst possible scenario, that the control ratio must be greater than or equal to 1.5, meaning that the control torque at its worst condition is still 1.5 times greater than the natural torque. These graphs you see now are the pitch control ratio conditions for the vehicle stages only within Earth's atmosphere. There are more graphs for the roll and yaw, as well as an entire other set for Mars landing and takeoff control ratios, but it's too much to show, so just take my word for it, they all remained at or above the 1.5 limit. The next discipline was the structures and weights discipline, and my job for this phase was to do two things: determine/place the center of gravity of the vehicle, as well as determine whether the vehicle is capable of surviving the loads, primarily by sizing structural elements, which in this case is primarily the stringers and the actual skin of the vehicle. Starting with the center of gravity analysis, I gotta say it was more tedious than it was difficult, because in order to find the center of gravity of the entire vehicle, you have to find the center of gravity for all the individual parts, like the payload, structure, piping, and so on, as well as their masses. This just results in a giant table of data, which you can then use in this equation to get the center of gravity location for the entire system. But there is a massive caveat. For a spacecraft, the majority of the mass resides in the fuel, because that is what is needed to be combusted in order to provide the thrust. And obviously, when you use up the fuel, the mass exits the system, and that changes the center of gravity. So, utilizing the volume of a cylinder, which is the approximate shape of our fuel tanks, we can utilize the mass fuel required of the engines to determine how much propellant and oxidizer are used throughout the journey. With the fuel usage, we can calculate the change in the volume of the cylinder, solve for its new mass and center of gravity. Put this all into a MATLAB code which solves for center of gravity locations from full to empty, and we get these graphs. Of course, the order in which I have structured this video is different than the order the project was completed in, because this data was actually needed as an input for the stability and control discipline, but you get the gist. Also, you might not have realized I made a massive oversimplification in my fuel center of gravity calculation. Earlier, I said that we can assume a cylindrical shape, and while that is true when the vehicle takes off for a brief time, it isn't always true. As the vehicle rotates, the fuel is pulled down and fits a new shape, which is no longer cylindrical. And even worse than that, the fuel sloshes, meaning that the volume is never constant at any point to accurately find the center of gravity location. However, like I said previously, conceptual design is meant to be a lower order solution method that gives enough accuracy in order to prove or disprove the mission and continue onto the next stages of design. And if you can't guess, modeling the sloshing of the fuel within the tanks during the mission operation requires heaps of time, which we didn't have much of, and resources, which shouldn't even be used at this design level. Now, before we get into the survivability aspect of the vehicle, let me just say that this, for me personally, was the bane of my existence in the entire project. I mean, this was by far the most conceptually and mathematically difficult process for me throughout the entire process, without a doubt. I'm just flashing some of the equations here just to show what I had to go through, but y'all gotta keep in mind, these images are from my final report submission, which is about 124 pages long, and this report is only a collection of my results after I had gotten them correct. I had pages and pages of just work outside of my report of me just sitting at my whiteboard, just trying to correctly derive this stuff, and believe me, it took a few tries until I finally managed to get it right. But when I did, boy were we finally cooking with fire. Again, just like everything else, there are a lot of stages to this mission, and I don't want to talk about each stage individually, so we'll talk about it in the most general sense. First, before you can find the survivability of the vehicle, you need to be able to determine the forces acting on it. This free body diagram is a 2D representation of what is all approximately acting on the body during its flight time. After creating the free body diagrams in a MATLAB code and then iterating through the flight phases of the vehicles, we can determine that the point at which the vehicle experiences the most forces is at maximum dynamic pressure during Earth takeoff. As such, here are the graphs of the forces and moments acting on the vehicle at that moment. Keep in mind the bending moments, as those loads, as well as the flight path angle, are what make the vehicle most likely to fail. With these forces, as well as the cross-sectional dimensions of the vehicle, we can calculate the stresses at the point in which the forces and moments are the highest. These stresses can then be used to create a stress matrix at the critical locations of failure on the vehicle, which are then used to determine whether our material of choice, ASI 304L, is able to withstand these stresses before yielding, with a 20% safety factor. Of course, whether it does or doesn't depends on the sizing of our structural elements. The team decided to maintain a constant 4mm thickness skin, which meant the only real structural element sizing came down to the stringers. I then ran all that mathematics with iterating dimension stringers in MATLAB to find out what is the smallest size stringers we need, and we can see the outputs with this graph. Like I mentioned earlier, it is the bending moment that is causing the most structural stress on the vehicle, and as such requires bigger stringers, with this line here being the dimensions that maintain that structural survivability for the least amount of area, and therefore the least amount of material, thereby keeping the vehicle at its lightest. Of course, we chose slightly beyond that line for safety purposes because it's dangerous to be right on the brink. Now, while I have discussed what I worked on for the course of this project, obviously, there are countless other disciplines like the trajectory team, aero team, propulsion team, cost team, and so on. And I'll even flash some of the results here, but I can't go into depth on them because I obviously didn't have any hand in making them as they were not within my purview. There are even things within my disciplines that have results, but because the team members within the disciplines compartmentalize into our own sections for the sake of time and efficiency, I only have broad knowledge of their methods, and I can't give a detailed explanations for their methodologies and derivations. I showed it once at the beginning of this video, but I'll show it again. These are the results of our reverse engineered Starship design, and as you can see, we are quite close to actual Starship values as made available by SpaceX. We do have discrepancies here and there, but that is all mostly due to our lower order model calculations for our vehicle compared to actual Starship, which has gone through much higher fidelity modeling, as well as actual modern day prototyping and build fly designing. This script was originally finished on May 27th of 2025, and I was going to get ready to record, edit, and post this video, but my senior design 2 class had started for the summer, which is just like this project, except instead of reverse engineering something, you're making something that doesn't yet exist. Of course, since you can see the published date of this video, you know that those classes have concluded along with our project, but I won't give you any spoilers, you'll just have to wait for the next video, which is much more exciting and hands-on, being that it was conducted in more of a bird's eye view compared to this project, as I was the chief engineer for that one, so I had my fingers in all the pies. Anyways, if you made it this far, thank you for sticking around to the end. I hope you enjoyed it, and if you did, you should definitely watch the next conceptual design project video, as it's just so much more fun in my opinion, so subscribe so you can get notified when that drops. For those of you who've been subscribed and waited on me to post, thank you. It actually does mean a lot, and I'm sorry I kept y'all waiting for so long. As you can tell, I've been really busy, and to be honest, I am still busy, but not as busy. So I do intend to make videos, although at a slower pace than I used to. Anyways, thank you all for watching, and I hope you all have a great day.